Fire behavior of composite structure. Abstract. In recent years, the use of steel concrete structure has increased significantly due to its advantages such as speed in construction, improvement in performance, protection from corrosion, etc. Several research are carried out to understand the behavior of such structure in earthquake, but not many on fire. This research mainly concentrates on the effect of temperature on the composite structure. A single-story structure consisting of encased steel column and concrete-filled steel column with composite beam with solid and filled deck were analyzed for gravity and temperature changes. The analysis were carried out by finite element method and American Institute of Steel Construction 2016 method. The result of the analysis shows that at ambient temperature both the column system behave similar to each other, but as the temperature increases the encased steel column system has better behavior. Also the beam's behavior was similar irrespective to the solid or deck slab system. Keywords: composite column, composite beam, composite frame, fire. Introduction. In recent years, the use of composite structure has increased significantly in India. Composite structure / member are member that are made up of two or more different material. The main advantage of composite elements is that the properties of every material are often combined to make one unit that performs better overall than its separate constituent parts. The most common kind of composite element in construction could also be a steel concrete composite. However, other kinds of composites include steel timber, timber concrete, plastic concrete, and so on. As a material, concrete works well in compression, but it's less resistance in tension. Steel, however, is extremely strong in tension, even when used only in relatively small amounts. Steel concrete composite elements use concrete's compressive strength alongside steel's resistance to tension, and when tied together this leads to a highly efficient and lightweight unit that's commonly used for structures such as multi-story buildings and bridges. The main composite elements in buildings are column, steel concrete beams and slabs. Composite columns can have high strength for a relatively small cross-sectional area, meaning that usable floor space can be maximized. There are several differing types of composite columns, the four most common being an open steel section encased in concrete or a hollow section steel tube which is filled with concrete. Steel reinforced concrete column, also known as concrete encased steel composite column, were studied extensively experimentally and numerically over the decade. However, the study focused on the structural behavior. In fire condition 1 to 3 and post-fire 4 to 5. For example, the effect of eccentric load 5, load 3, restraint to thermal elongation 6, axial restraint 7 to 8, effect of three-sided heating 9. Further, the SRC were compared with steel reinforced ultra-high toughness cementitious composite column 10. Concrete-filled steel tube fire resistance is influenced by cross-section shape, size 11, axial load 12, three-side heating 13, strength of concrete 14. Hai Han et al. 15 studied the flexural and compression behavior of CFST. Various type of CFST such as concrete-filled double skin column, double tube hollow steel column 16 to 17, CFST with steel core 18, concrete-filled rectangular hollow section 13, elliptical concrete-filled steel column 19, RCC confined with steel tube 20 were studied. Yang et al. 21 studied the post-fire behavior of CFST column. Analytical modeling 22, numerical modeling 23 to 24, and nonlinear analysis 25, 26 were studied for SRC and CFST column. Composite beams are normally hot-rolled or fabricated steel sections that act compositely with the slab. The composite interaction is achieved by the attachment of shear connectors to the highest flange of the beam. These connectors generally take the form of headed studs. Most of the study of composite beam focused on the effect of restraint 27 to 29, and shear tab / connector 30 to 33 in the fire condition. Composite beam were studied experimentally 34 to 35 and by OpenSeas 36. Castellated beam 37 and cellular beam 38 were also studied for effect of fire load on them. Modeling of composite beam is studied ROM 39 to 4. Composite slabs are typically constructed from reinforced concrete so top of profiled steel decking, reentrant or trapezoidal. The decking is capable of acting as formwork and a working platform during the construction stage, also as acting as external reinforcement at the composite stage. Studies showing the fire behavior of composite slab to fire 41 to 54 were reviewed. Composite structure consisting of various orientation and condition were studied 55 to 64 for fire. The study aims to model a composite structure using analytical and numerical method for gravity load and temperature changes. The software used for the analysis is ETABS 2018 and numerically by AISC, American Institute of Steel Construction, 360-16. After the analysis both the results are compared. Femi Analysis. A single-story composite structure of dimension 22 ma 22.2 m and floor-to-floor height 3.6 m subjected to gravity and temperature change. The modeling is done using ETABS 2018 software. Load considered are self-weight of member and a uniformly distributed load of 12 kN/m2 and a temperature change from ambient temperature i.e. 25C to 525C with an interval of 100C. Loads and its combinations are considered as per minimum design loads and associated criteria for buildings and other structures, ASCE/SEI 7. Two types of composite column is used, viz. Encased steel column and concrete-filled steel column, both of dimension 609 mm AA 609 mm. The section used for composite girder is W24AA 94 and composite beam is W21AA 62. The slab is of 190 mm thickness. From the above table we can say that the bending ratio of composite beam and composite girder subjected to temperature change of analytical result are slightly different from numerical result. The decrease in the moment carrying capacity at elevated temperature is calculated by using the retention factor, whereas in analytical method the decrease in capacity is calculated using dm, which gives more accurate result. This can be due to more conservative values, i.e. retention factor used in numerical analysis. At 25C the difference between shear ratios is equal for composite beam but difference is more for girder. The difference between the analytical and experimental is approximately 20% for composite beam and girder. V. Conclusion. Considering above result, following conclusion may be drawn. Irrespective of the slab type, i.e. solid slab deck or trapezoidal filled deck slab, the shear ratio, deflection ratio, and deflection for composite slab and girder is similar. At 25C the difference in the shear ratio is low for composite beam but it is more for composite girder. For encased column system, the demand/capacity ratio at ambient temperature is low, i.e. 0.153, and as the temperature increases, the demand/capacity ratio also increases to 1.751 at 525C. For encased column system, the demand/capacity ratio at ambient temperature is 0.345, and as the temperature increases, the demand/capacity ratio also increases to 2.345 at 525C. For given load condition, the encased column system is more thermally resistant than the concrete-filled steel column.